Fairly often, I get asked questions about how I got started podcasting with the Breaking Math podcast, and I'll often be asked this question by those who are thinking of starting their own podcast. That is, people who are looking to tell a story or share their unique wisdom with a larger audience or their passions, or maybe just advertise their business or services. I usually like to start this conversation by either showing off or telling about our preferred podcasting platform, Zencaster. Zencaster is essentially an all-in-one podcast hosting platform. On this platform, you can do everything from recording your episodes to editing your audio and video files to distributing your podcast to all podcasting platforms, including Apple Podcasts, Spotify, iHeartRadio, and wherever else podcasts are played. Now, there's more. When I first began podcasting, I used to get very nervous about how I would sound. I would sometimes stutter or have awkward pauses or other audio blemishes in my recordings. Now, Zencaster has a new suite of AI tools in their post-production process that make you sound really smooth. They automatically take out any of the ums or ahs in your recording. Also, they automatically take out any of the awkward pauses in your discussions. The tools will also help you set the right loudness and balance all the levels while reducing any background noise, all with the click of a button. Doesn't sound too bad, does it? You really should check it out. Really, the world needs to hear what you have to say. In fact, I'm going to give you a code below to help give you a large discount. It's all one word, Breaking Math. Go to zencaster.com/pricing and use my code Breaking Math, and you'll get 30% off of your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting content needs. It's time to share your. People very often ask me both how and why I started my podcasting journey. Well, as an engineer, I'm frankly very passionate about math. I wanted to find somewhere to share stories of great mathematicians from Archimedes to Alan Turing and everyone in between. And for that reason, I want to tell you a little bit about my preferred hosting platform, which is Zencaster. Now, before I continue, this is usually the conversation I have with anybody who is wanting to start their own podcast. I know there are so many people out there with passions that they want to share with the world or unique knowledge that they're just looking for a platform to start with. And Zencaster is a wonderful all-in-one platform. What I mean by that is you can do your recording and your editing and use AI to create a transcript and distribute to all platforms, including Apple Podcasts or Spotify or anywhere else where podcasts are played. For anybody like me who might worry at first about what you might sound like on an audio recording, Zencaster's post-production process makes you sound really, really smooth. It automatically removes any of the ums or ahs in your recording. It removes any of the awkward pauses in conversations, and it also helps you to set the right podcast loudness and levels while reducing any background noise, all with the click of a button. It couldn't be easier. Go to zencaster.com/pricing and use my code BREAKINGMATH, and you'll get 30% off your first month in any Zencaster paid plan. I want you to have the same easy experience I do for all my podcasting and content needs. It's time to share your story.
So here at Breaking Math, of course, very often we like to talk about all things math and society, but we also have another interest. Occasionally on our show, we'll have a guest on who has a specific experience with math education or STEM education, and we like to bring on guests who may have a unique perspective on things like education in STEM, which is science, technology, engineering, and mathematics, and that's what we're doing on today's episode. Today I'm interviewing a student named Frank Salas, who is currently a PhD student in electrical engineering at the University of Michegan, and he's also a recent graduate of the University of New Mexico, also with a bachelor's in electrical engineering. And Frank has quite a story about what got him interested in electrical engineering.
Frank Salas is a statistical exception, but far from an irreplicable result. Busted on the streets of Albuquerque for selling crack cocaine at 17, an age where many of us are busy honing the skills that we've chosen to master, and promptly incarcerated in one of the myriad concrete boxes that comprise the United States penal system. There he struggled, as most would in his position, to better himself spiritually or ethically, once even participating in a prison riot. After 2 stints in solitary confinement, he did the unthinkable. He imagined a better world for himself, one where it's not all him versus the world. With newfound vigor, he discovered what was there all along, a passion for mathematics and the sciences. After 9 years of hard time, he graduated to a halfway house. From there, he attended classes at community college, honing his skills using his second lease on life. That took him on a trajectory which developed into him working on a PhD in electrical engineering from the University of Michegan. We're talking, of course, about Frank Salas, a man who is living proof that condition and destiny are not forced to correlate, and who uses this proof as inspiration for many in the halfway house that he once roamed. So who is he? What is his mission? And who is part of that mission? And what does this all have to do with Maxwell's equations of electromagnetism? All of this and more on A Breaking Math. Episode 13, Math and Prison Riots. I'm Jonathan.
And I'm Gabriel.
And as you heard at the top of the show, our featured guest today is Frank Salas. Frank, would you like to introduce yourself?
My name is Frank Salas.
Frank has quite a story about what got him interested in electrical engineering. Frank, I'd like to talk to you a little bit about your story, specifically your education and what made you choose the path that you chose.
So speaking from when I was in college, I originally started out, I wanted to major in linguistics. And I took pre-calculus just kind of for the fun of it because I needed some more credits when I was at CNM. And I took it with Judy Lalani. I'm sure you had her for some classes at CNM.
Yes. In fact, I had her from MATLAB, and she actually is a follower of the Breaking Math podcast. Hi, Miss Lalani. How are you?
Well, she knew my backstory, which we'll get into, and she kind of forcefully told me, you are not doing linguistics and you need to look at physics and math. And I did, and I, found out I liked it, and I was sometimes good at it.
How cool, yeah. Miss Lalani is, of course, as Frank said, a math professor and sometimes a MATLAB professor at CNM, and she's very passionate about math and very passionate at her students, so she's quite awesome. Yeah, so now actually I'd like to talk to you a little bit about your backstory, and this goes basically a little bit into your formative years, let's say, as a teenager, as well as an adult, and as recently. Can you tell us about your attitude toward education and about your life experience, let's say around age 17?
So I'm currently 34. I started college when I was 29. So the question is, why did you start college so late? And the answer to that is I spent my 20s in the federal prison system. From 20 to 29, I was in the federal prison system for drug charges. And that started in 2003 till 2012.
Now, I've heard that there's not much reform to be found in the prison system. So why do you think you found reform in it? Or was it your experiences from the prison system, or is it your experiences despite the prison system?
So mostly my experiences, I would say, despite the prison system. But so, growing up as a teenager, I was kind of wild and what some people would term a knucklehead. My wife doesn't like when I use that term because she thinks people don't know what it means. But that's what I was as a teenager, and that's why I got involved in the things I did and what sent me to prison. But also going to prison, it's not like you immediately you have the handcuffs on and immediately you're changed. I went through years while I was incarcerated where I was still wild. And there was a period in 2007, I was in a facility in Big Spring, Texas, and there was a huge prison riot, and I got grouped in with a bunch of guys, and they sent us to a lockdown unit in Oakdale, Louisiana. And at that point, we stayed there for about 11 and a half months, close to a year on lockdown, and needless to say, I had a lot of time to think, and that's when I first started to kind of contemplate my life and sort of think about other things to do.
Now, for those unacquainted, can you describe what lockdown is?
Lockdown is 23 hours a day for 5 days a week. The other 2 days, you're 24 hours a day just in your cell. So when I say 23 hours a day, you get 1 hour of recreation, and that's like in a cage the size of a bedroom, maybe, that you get out for rec during the weekdays. And then you get a shower 3 times a week. And the showers are usually located, down on the other side of the unit, and you're handcuffed to the shower. The shower's in a cage. Take a shower, go back to the cell. So you're basically just in the cell all day, every day.
And was it this time that you found time to read or just to think?
I had time to think, but on a deeper level, I had time to look within instead of without. And what I mean by that is I was able to truthfully and honestly ask myself why I went to prison, and not the surface, superficial reasons of course I was, selling drugs, but on a deeper level, why did I do the things that I did on a psychological level, and to kind of psychoanalyze myself. And that was what allowed me to truly change my outlook and what I wanted to do in life. And then once I left there, I was sent to Kentucky. I had the opportunity to be a cellmate with a guy who, he had been locked up like 20 years, and he was into studying languages. And so kind of under his wing, I started looking at languages, and I started to study Spanish and French. And that's what got my idea of, okay, I'm going to get out and go to college, and I'll study linguistics because languages are fun. But fortunately, I found a different language to study, math.
Check out episode 6, Word. But
Also, check out episode 5, Language of the Universe.
But so would you say that this individual, your cellmate, had a big impact on you, or were you already headed that way?
I was already headed to, not getting out and committing crime. And I know that might sound easy for some people that aren't in that situation, but it takes a lot to truly be honest with yourself on what you're going to do, whether you're in prison or whatever you're doing in life. But having the interactions with him is what implanted the seed that, maybe I'll try college when I get out. Because when I got arrested, I didn't have any technical skills, no trade skills, no work experience. So there was a sort of nervousness of getting out. What was I going to do? I didn't have any skills. I didn't have any financial cushion.
So when you got out, what was your game plan? Did you have one at that point? Or were you formulating it the entire time that you're in?
I was formulating it like my last couple years. I wanted to go to college, and I know that sounds vague, but that was my game plan. Do what I have to do to go to college. And so when I was released to the halfway house, where I stayed there for 6 months, and my first pass to leave the halfway house, I went down to C&M and went through their process to figure out how to get enrolled. And luckily, I qualified for the Pell Grant, so I was able to start. I got out in February. I was able to start classes that summer.
Now, for those unacquainted, and myself included, can you tell us a little bit about the rules, regulations, stipulations of a halfway house, and did that make it more or less difficult for you to start college?
The halfway house makes it difficult for people who don't want to behave, and they want to experience like catching up on old times type of mentality. Me, I was on a mission when I got out. First I wanted to go to school, but like I said, I didn't have a financial cushion, so I needed to set myself up financially. I wasn't trying to look for the greatest job or the highest paying. I just wanted a job. I went and I was able to get a job at Long John Silver's, fortunately, because I didn't have anything when I got out. I had literally the clothes on my back. So for somebody like me who was motivated to do something like that, the halfway house was super beneficial. I had a bed to sleep in, and I had 3 meals a day. And then I can go out and look for a job and things like that.
So would you credit the educational system, mathematics, or physics, or what would you credit with your current life success? Or would you just credit your own spirit?
I wouldn't be selfish and just say it was only my own spirit. I would say the sort of wonder of math and physics is what inspires me to move forward. There's, no matter what you study in these fields, there's like always so much more. And it's like the deeper you get, there's just even more. It's like pulling that string on the end of a sweater. The more you pull it, you're just unraveling more strings, and you can, never get to the end.
One of the things that I want to ask you about actually is during your time, whether it was incarcerated or the time in the halfway home or even afterward, were there any books that especially had an impact on you, both for your appreciation of mathematics or your appreciation for physics?
So I read a book called The Self-Aware Universe. This was while I was incarcerated, and it was written by a theoretical physicist named Amit Goswami out of the University of Oregon. And what he does is, the first half of the book, he kind of breaks down quantum mechanics for the layman. And then the second half is he equates those ideas to his spiritual views. He's a Hindu, and so he kind of tries to bridge his spiritual views with the quantum physics. Now, I'm not really a spiritual person in that sense, but just even I had never been exposed to quantum mechanics in general or much physics in general, and just like thinking about things, these far out ideas that I had never heard of, really piqued my interest of just, education in general, and just kind of learning things that like I had no idea that there was stuff like that even out there. And it just kind of opened up a lot of, mental doors of what to look for. And
one of the things I also wanted to ask you is, having it made it as far as you have on your journey, I'm quite curious what you might say to others who are in a similar situation to yourself, but who aren't as far. Say those who are either incarcerated and looking to being on their way out, or those who are in a halfway home. And I realize this is not a math-related question. What would you say to them?
So I would say the number one thing that allowed me, and I know, this is specific to me, so it might not apply to everybody, but I can only speak of my own experience. The number one thing that allowed me to completely change my outlook and what I was going to do in life was to truly let go. And what I mean by that is to let go of, like, let's say I was incarcerated for selling drugs. So let go of the guy who ratted me out, for instance. Like, who cares about that? A lot of people have a hard time doing that. Or, I missed out on my 20s where a lot of people are, say, going to the club and partying at bars. Well, I needed to get out and set myself up financially. So I didn't have time to go out and catch up on, the quote unquote old times with people, and to let go of old friends. And I know that might sound kind of cold-hearted, but a lot of times those old friends are still doing the same thing. And so to just completely let go of those things and to just focus on yourself and be selfish with yourself and your goals can allow somebody to move forward.
I've heard that in prison they have really, really kind of crappy bologna sandwiches. Is that true?
It depends where you're at. So I was in the federal system, so some places had good food, some places had bad food. It really depends on where you're at.
What discipline within electrical engineering are you studying?
So applied electromagnetics, and that's also pretty broad. Why
don't you break it down for someone who's like never heard of it before?
So what I specifically am focusing on is wireless power transfer. So picture like you can go buy these little docking stations for your cell phone to charge without plugging in. Mm-hmm. That same type of concept. And the applied electromagnetics, for somebody that doesn't understand, would maybe be like how satellites talk to us down here on the ground.
Interesting. So wireless power transfer, I've heard of this. Is it correct that Tesla designed the precursor to wireless power transfer?
And just to clarify, wireless power transfer is not to be confused with free energy or anything like that. There's no such thing as free energy.
No, not at all. There is no free lunch, as many teachers like to say, right?
Oh, yeah. Absolutely. I was just thinking of the basic idea of like charging something from a distance, which is a really cool idea, right?
Yeah. So, there's people now that they create these supposed free energy things, but what they're doing is wireless power harvesting. Mm-hmm. And so, you have tons of signals going, radio stations and whatnot, and there's energy associated with those signals, and they just basically harvest that energy and then say, look, I have free energy.
Nice.
Background energy harvesting.
So for those who love to speculate about the future and what technologies are coming down the pike, what are some technologies that we may see in 5 years, 10 years, 100 years if this technology is fully realized?
With autonomous vehicles, charging cars, you can have, say, in the asphalt somewhere, a wireless charging, I'll use the word pad for lack of a better word. And then, of course, you would have something in your car, and where you just park above that. And then also, for like, say, small electronic devices in your house, you'd have some central unit that charges your devices.
So I also studied applied electromagnetics when I got my master's degree in electrical engineering.
Yeah, we took antennas together with Tarif.
Oh, Professor Tarif, he was phenomenal.
Yeah, I like Tarif. He wrote a lot of letters for me to get into grad school.
That's awesome.
Now, Frank, you wanted to talk a little bit about Maxwell's equations. Can you break those down for us a little bit?
So there's four Maxwell's equations. Okay, so let me backtrack a little. So Maxwell, in his treatise where he developed his ideas, there was actually, I think, like 18 or 20. And then you had another mathematician, Heaviside. I don't know his first name, but he's the one that broke them down more concise to the four equations that we know of.
And for our listeners, a lot of the common calculus notations that you see all the time in a calculus course was really because of Maxwell. They weren't really necessary until he came out with his like engineering stuff, especially with things like divergence, which is not very popular until Maxwell came around and needed it for his equations. Is that correct, Frank?
I don't know if that's correct, but he definitely was in favor of what's called the differential form, and that would be like the divergence curl notation.
And we will break those down in just a moment. They went from 18 to 3 equations, you said?
4. There's four. You actually only need 2 of them there's 2 that are completely independent. The other 2 can be derived from the first 2. And then there's what's called the continuity equation, which also goes with them. So, Maxwell's equations are thought of as 4, but actually there's 5, and that includes the continuity equation.
So let's break it down. What's the first one that you'd like to talk about?
So the first one that's typically listed is Gauss's law of electricity, which basically says that the divergence out of a specific geometry equals to the charge.
Quickly, though, for listeners who are less familiar, perhaps those of high school age, how do you explain what divergence is? You can use any analogy at all.
Like, say, water going through a pipe, and if we take like a cross section of the pipe, like what water is flowing through that cross section at like a point in time or something like that.
Yeah, I read in Maxwell's treatise, and he calls it an unimaginable fluid or something like that, because it's like a fluid, but it has different properties than water, because water is not compressible, things like that.
No, yeah, I'm just saying, just to think about like, something moving through a specific, like the cross section, like I said. Yeah, you're right. It's not the same as water.
Jonathan, didn't you read the Feynman undergraduate lecture series in physics, the one specifically about electromagnetism?
Yeah, I did. I did a little bit ago. Feynman does like an amazing job talking about all this stuff. If you want to learn electricity, there's almost nobody better than Feynman.
Yeah. I got to say, I love the way Feynman explains it, and I really love his analogies. In fact, my goal for this podcast in general and for this segment is to make it really easy to understand so that anybody, my nephew, my grandmother, anyone regardless of their background can understand this segment.
So let's break it down even further then. What's electricity?
That's a good question. So, you can't directly measure an electric field, right? That's something that's indirectly measured through charge or current.
So let's break it down even further. I'm sure that anybody here who's listening to this podcast has encountered charge. You do things like charge your phone. But what is charge?
So if we break it down further to the electron.
Can you break down charge even further? Are there individual like atoms of charge, so to speak?
Yeah, so within an atom, of course, you have proton, neutron, electrons, and so with electricity, we're thinking of the electron. I mean, you get into other concepts like with semiconductors, and you talk about positive charges, which are holes, but like for simplicity, think of the electron when talking about electricity or currents.
Now, what we are referring to here is actually the movement of individual electrons, which is what electricity is.
Oh yeah, and that's what I was getting to. It's the fact that there's almost a universal sense in which electricity cannot be broken down further.
So there's actually a new fun segment that I really like that we're going to do in Breaking Math, and it's kind of one of these hypothetical questions that we like to talk to people. Essentially, the purpose of this kind of question is to say, if you had unlimited funding and all the curiosity and wonder that you have right now, what would you like to research? What would you like to invent? What would you like to see built?
I don't know about an invention, but as far as research, I would like to look into the electrical signals produced by the human body, and not just restricted to the human body, but just by biological organisms in general. What type of signals are being produced, what frequencies are being produced, and how can those be utilized? Like, I mentioned wireless power harvesting before, because people make devices that harvest electromagnetic power that's already out there. Just looking at the signals that are produced by biological organisms.
Do you think, in your opinion, and I don't know too much, but I mean, during the recording we have breaks, and during the break you're talking about reflection and S points, S signals,
S parameters.
Do you think that would have anything to do with modeling the nervous system better?
Perhaps it depends on. So I mean, the S parameters are a fundamental concept. With dealing with high frequency circuits,
which does not describe the human brain. I mean, well, maybe it does. The human brain, the signals travel about 300 feet per second. So, could the fact that they switch it on and off a lot faster than that, could that be modeled as a high frequency circuit? Like, I don't know.
I'd be reluctant to say one way or the other.
No, you have to say.
Yeah, I don't know, because like when I think of like AC circuits and it's the AC frequencies, I just think of like the the spinning, the quick back and forth. So I don't know. I mean, I honestly, again, we're gonna have to ask a biologist this or somebody who's familiar with the nervous system about the back and forth, of the signals in the nervous system. I'm not sure.
Well, there's an idea that's kind of theorized that cells communicate using RF. Now, it is known that cells communicate using electrical signals. I'm not a biologist, so I mean chemical
calcium
signals.
Channel, all that.
Yeah. Well, so if you think of like biofilms that are formed on rocks in a river, as the river's flowing, they're obviously, you're not going to be able to have a chemical channel for these cells to communicate. So it's kind of theorized that they're using RF when they form these chains to make this biofilm. And that's sort of a area of research that some people would like to do. I don't know if there's a whole bunch in there, or it hasn't been proven that they do.
During the pre-interview, yes, we did do a pre-interview interview. One of the things that you had said, Frank, is that what really fascinates you is the electromagnetic spectrum as a whole. I think I don't know anybody who is aware of the electromagnetic spectrum who's not fascinated by it.
Something that fascinates is just the idea of frequency. Like even the electricity coming out the wall is 60 hertz, so that means that it flips from positive to negative 60 times in 1 second. As fast as you snap your finger, it's 60 times. Now your computer is, let's say 4 gigahertz. That's a billion times, 4 billion times in 1 second. I don't know. For some reason, to me, that's just fascinating. That we can even measure it also is fascinating.
One thing that fascinates me, bringing that up, is just the fact that there's such a qualitative difference between the different frequencies. Like you have gamma rays, which are completely different in character to light waves, but they still have so many similarities. And then you have like theoretical electromagnetic waves that nobody has any idea of how to produce because they're so low frequency.
I almost think that we could have a whole episode on just the electromagnetic spectrum. I don't know, just a thought.
Well, we are going to have an episode. Stay tuned, everybody, in several episodes about frequencies.
And Frank, I want to bring up something else as well. When as we're talking about the electromagnetic spectrum, but we're also talking about other things like biological processes. So obviously, we know our eyes. What's the frequency of the visible light spectrum?
It's about 10 to the 14 in magnitude, 10 to the positive 14, and so the wavelength is between mid 400 nanometers to about 700 nanometers.
Right. Yeah, in that range. That's just a given frequency. Yeah, and we get all of our visual information, rather the visible light spectrum as we see all those. We don't see anything in the ultraviolet. We don't see anything in the infrared.
So that's an interesting an interesting topic. That's also the life-giving quality of water, because water has at the visible spectrum, it resonates.
What you're saying kind of reminds me of a treatise by Goethe on it's called On Color or something like that. I would encourage all our listeners to check that out. It's one of the last totally qualitative scientific texts.
I've read a couple of books. So, I mentioned the visible light spectrum, but there's a book that I read that's a fascinating one, and it's based on physics research and biology research, and I don't know that it is a true story. It's slightly embellished, as a lot of stories are. The book is called The Emperor of Scent, and in this book, it is about a physicist who met with a lot of chemists and You can already tell how I'm setting this up here. These chemists work in the perfume industry, and they've got models for how the sense of smell work. And according to their models, the sense of smell, what we experience as smell, and differences in different smells of fancy perfumes are based on the shape of the molecule. The physicist has a lot of experience in the electromagnetic spectrum, specifically in RF frequencies, and he postulates that it is actually the vibrations of the molecule and the RF, the radio frequency waves that are made from the movement of electrons in the molecules that in fact produce the smell. And it's never completely proven. It's almost proven, but it is not proven conclusively. But it's just fascinating because in an upcoming episode, we're going to do, no spoilers here, but, we're going to talk a lot about human consciousness. And we're going to talk about how we get information from all of our senses and to really realize how many of our senses and how our information in the universe comes from vibrations in the electromagnetic spectrum is just fascinating.
And if that seems a little bit far-fetched, especially because we don't have language for stuff like smell, consider the fact that philosophers, until the thermometer was invented, considered temperature to be something too complicated to be described by a single number. They thought there was a difference between bitter cold and, like, icy cold, all these different things. Yeah. So Maxwell's first law, could you explain that in the simplest terms you can?
So explaining it in the simplest terms is something that I myself struggle with. So I'll try. Maxwell's equations are written in two forms, the differential and the integral form. So the differential form says that the divergence of the electric flux equals the charge going through a surface. So the way I like to think about that is like if we had a pipe with some water flowing through it and we just cut that pipe at a specific cross section, and the flow through that cross section would be the divergence. And I know water is not comparable to electricity, but just like an analogy.
Yeah, but let's break that down a little bit further. Take me on a mental journey on the kind of fluid that, because I know that electricity used to be called the electric fluid back in the early days. And why is that?
So I don't know why is that. Maybe that comes from the time when they thought there was an ether or something, but the electric field is created from charges, a positive or a negative charge, and these can be associated with atoms that have one polarity, a positive or negative.
Now let's go into the positive and negative thing a little bit. I'm not an electrical engineer, but I know that there's something that has to do with them being the wrong way around, kind of, right?
So what do you mean by wrong way around?
It doesn't flow the right way that people assume?
I think what you're referring to is conventional current. Is that right?
Yeah, so the electron itself doesn't move in the direction that the current moves, if that's what you're thinking.
I think that is. And could we break that down for everybody? Because what I want to break it down to is a point where, electricity looks like magic.
It does look like magic, and that's kind of what attracts me to it in a sense. So, like if you have current, and we'll think of, I'll loosely say current as electricity. The current flowing through a wire isn't like an electron flowing from one end to the other. You could think of it as a line of people, and one person bumps into the next person and it just follows along the line like dominoes. An actual electron flows really slowly. Like you can actually calculate that. And
how slow are we talking?
So the speed of light is 3 times 10 to the 8 meters per second.
Yeah.
I would say maybe 5 orders of magnitude less.
So let's say that the speed of light is like a car on the freeway. This would be like a snail or something.
Yes.
Okay, yeah. So basically, to recap for our listeners, since the time of Maxwell and of course his contemporary Faraday, who is actually buried right next to Isaac Newton, they were essentially the founders of this field of physics, and so essentially we were discussing how with electrical engineers they knew about current and they had conventional current, which actually is the opposite of the directions that electrons flow, but also. As Frank, as you said, a current is not a fast process. It's a very, very slow process. That's utterly fascinating. So So the energy of a current, it's, I don't know. It's,
Well, the current itself is fast, but the movement of the electron, or what's called the charge carrier,
right.
that
Yeah.
itself isn't, relatively speaking, isn't fast.
Yeah, and a big part of that is you have a current in something like copper, but that's obviously a metal where we've got electrons that are more like bees on a hive, unlike a non-metal. Where for our listeners, how would you describe the electrons on a non-metal? Like apples on a tree. I'm sorry, that just came to me, and I totally interrupted you. But like they're more like apples on a tree, right? Like they're kind of stuck in place.
Yes, yeah, that would be a good analogy. They're stuck in place. There's not a polarity, if you will, a positive or negative charge as a whole.
So the charge has to do with how many electrons there are, or what are we measuring when we're measuring charge?
So like if we have an atom and it's you have shells to an atom that hold your electrons, and if you have a shell that has less than the amount of electron that is required to make a complete shell, then it's positively charged. If you have an extra electron, then it's negatively charged.
Yeah. So one other way to think about it, when I taught eighth graders, we learned a lot about chemistry, and you can think about it like vacancies on a bus. Like if you've got some vacant seats, you can think of that as a net positive charge, assuming that all the passengers are negative, because I guess people who ride are negative people. I mean, charge wise, not attitude wise. So if you have a bus and every seat is filled up, that's like that's the equivalent of a neutral atom. And then a net negative atom is if you've got too many people, then everybody's negative, right? And you've got a net negativity because you've got more. If an empty seat is a positive charge, you've got more negative charges than you do positive charges. I think that works, right?
Yeah, that works. And I think that one thing that I want to get back to is Maxwell's laws, and then after we talk about Maxwell's laws, we're going to talk a little bit about the history of electricity. But Maxwell's first law, you're saying that the amount that the electric field, and electric field means something different than charge, correct?
So I'll backtrack a little bit. So the Maxwell's equations, he did not derive those. So the first one that we talked about is Gauss's law of electricity. What Maxwell did was group all of these equations together, and he found a relationship between between electricity and magnetism, and was able to group these equations together. And his important contribution is why these equations get named after him is what's called displacement current, and that was what was attached to Ampere's law, because Ampere was the one that derived that law, which says that if we have a magnetic field around a wire, then we'll have a current associated with that magnetic field through the wire.
And an experiment they could do is with a compass, correct?
Yes.
Yeah, you just take a wire and you put a compass next to it, and if there's stuff flowing through the wire, then the compass, what'll happen to it?
It'll deflect, and what that means is it'll be pushed by the magnetic field in one direction or the other.
What I also really love is that during Faraday's time, when he was talking about these fields, he was actually met with a lot of resistance, no pun intended, with electrical engineering, because people didn't like the idea of this invisible field that had an effect. But through his experience, his experiments, along with the experiments of other people like Volta in Italy, he showed that this electric field certainly exists.
And it's one of the basic properties of the universe, right? The electromagnetic force.
Yes.
It's basically in the DNA of the universe, kind of like as we know it currently. That there's just something called the electromagnetic force. Or electromagnetism.
Frank, just out of curiosity, do you know much about the unification theories of any of the forces?
I don't. I don't. It's something that I've wanted to look more into. But electromagnetic force is the most well understood of the forces in physics. Yes,
even though there's gravity, and even though Newton discovered gravity, we know less about gravity than we know about electromagnetism. And again, just for our curious listeners, this is a really cool part of physics, So we recognize gravity, we recognize the electromagnetic force, we also recognize two other ones. We later learned about the weak nuclear force and the strong nuclear force. What I'm talking about, the unification, in the 1960s or the 1970s, there were two physicists who proved that in the early universe, the electromagnetic force and the weak nuclear force were one and the same thing. And that happened at a very, very high temperature and very, very high pressure. And then only after the universe cooled down and spread out did the electromagnetic force decouple from the weak force. I just find that fascinating. Now, since then, people have searched, but there hasn't been any discoveries or any proofs that talk about a grand unified theory that really brings all four of those forces together. I just think it's really cool that bit was discovered.
Oh yeah, and just to clarify, some people are going to be thinking, well, we know a lot about gravity, and that there really is the case if you're talking about on a big scale. Have you studied much in the way of general relativity?
No, I took physics at UNM called Physics 3, and we did some relativity stuff, but I wouldn't say it was enough to say that I know relativity.
One thing about general relativity is that you have these forces. It has to do with the flow of momentum in 4 dimensions, where one of the dimensions is time. I mean, we have these amazing formulas that have extremely good predictive power. But as we understand it, forces are supposed to have particles that exchange them, and we have not found a particle for gravity.
Yes, this is true.
This part always confused me because I have not taken all the physics that I need to take in order to fully understand this. You know, I know that when you get into Einstein and relativity, gravity is often thought of as just a bending of space and time. You know, and I know that goes along with general relativity, but then, you know, that says nothing. You don't even learn about a particle exchange with gravity with that.
Well, one thing that people a lot of times neglect to realize is, or just don't realize, is that there's also a bending of space and time that happens with electromagnetic forces. A beam of light creates its own gravity, in a sense. So if you could really look at it in a grand sense as almost being the same thing, as electromagnetism in a weird way.
Oh, okay. So really, like, you know, Einstein's theories, although we apply them to gravity with the gravitational constant, they can really describe any forces.
Yeah, in a way. You have the Einstein tensor on the left-hand side. This is going to get a little bit technical. And you set it equal to the stress-energy tensor. Now, electromagnetism has a specific stress-energy tensor that deforms the universe in a specific way. What is another one of Maxwell's laws?
So we talked about Gauss's law for electricity, the electric field, and we have Gauss's law for magnetism, which says that a magnetic field, the flux of a magnetic field through a surface equals 0. And what that means physically is that you have a north and south pole, that a magnetic field will always come back in on itself. You don't have what's called a monopole, or with electric field you have like these opposite charges.
One way that I like to imagine electricity, and tell me if this is accurate at all, because this is kind of rubber meets the road moment, is imagine you have bees the size of grains of sand, and they're flying all around, and that's your kind of like, that's your field, right? And you have a certain amount of charge, which is like the hive, and you have like a wiffle ball where the bees are flying in and out of the wiffle ball. Now, if it's magnetism, then the same amount of bees are always flying in and out of the wiffle ball at the same time.
Yes, I would agree with that analogy.
Well, yeah. This is a fundamental constant. So just to break it down, you know, you've got electromagnetism. Let's talk, you know, you've got electrons and you've got magnets. And then, of course, again, as you said, anytime you have a North Pole magnet, you always have a South Pole. And then this is just saying exactly what you just said, but in other words. What was fascinating is I saw, you know, a couple of physics professors once upon a time make a bet that there never will be a magnetic monopole. You can go find a single positive electron, but you can never find just the North Pole lying around. You'll always have a North and South. Now, I got to witness a student bet the professor otherwise, and the student presented the professor with a paper that talked about a group of students that created a magnetic monopole using a Bose-Einstein condensate. Essentially, if you get a whole bunch of magnetic groupings of atoms, I'm sorry, I'm blanking here, and you arrange them around a very, very, very cold Bose-Einstein condensate, then technically speaking, you won't have the south pole of the magnet. I thought that was pretty clever. That's completely artificial. And again, depending on whether you want to define that as true or not, it was a clever challenge to the professor. What would you say, Jonathan?
It sounds a little bit like trying to make a black body by getting a bunch of velvet boxes and putting them within one another. It's not really going to be a black body. It sounds along the same lines to me, but I don't know enough about this.
Well, in electrodynamics, you use the concept of a magnetic charge for a lot of calculations, like with aperture antennas and things like that, a magnetic current, things of that nature, which don't technically exist, but you use them for your calculations.
Now, before we get too far into this, a lot of people, everybody's familiar with lodestone and its properties, but a lot of people don't understand that it wasn't understood for a long time that magnetism and electricity were related. Can you explain the similarities and differences between the two?
So, Gabriel had alluded to it earlier when he mentioned Faraday, who was arguably the greatest experimentalist to ever live. And he's the one, I believe, don't quote me on it, that first noticed the dependence on each other of electricity and magnetism. And which is Faraday's law, says that the curl of the electric field equals the time-changing magnetic field.
And a curl is basically, you can imagine this like if you ever have swirled around water, where there's eddies in the water. If you imagine that going around an axis, the line that describes where the eddies are is the curl, correct?
Yeah, like a whirlpool.
So basically a curl curls?
Pretty much.
Yeah. Thank you. I was holding onto that for a long time. I'm glad I got to say it. Yeah. So yeah, and then of course with Faraday, again, as we said earlier, you have a traveling electric current through a wire, and from that you have a stationary magnetic field.
So that's I think you're getting to Ampere's law, where if you excite a current through a wire, that current will create a magnetic field around the wire.
Now, Frank, for some of our listeners out there who might be interested, what is it like getting a degree in electrical engineering? What kind of classes do you take? That kind of thing.
So, to begin, it's hard. You take a lot of math, and you take physics classes through the physics department, but I would say that all of the engineering classes that you take, whether it's electrical, mechanical, are all physics classes. Because that's what drives what you're doing is the physics.
So describe a couple of classes. Describe some of your favorite classes and some of your least favorites.
So I'm in grad school for applied electromagnetics. So obviously the undergrad version of electromagnetics is what piqued my interest ultimately to go further in that. But also partial differential equations in the math department. That was like the first time I really felt like I was doing some really hard math. And of course, it was the undergrad version, so it was probably watered down also.
And partial differential equations, for those who are interested, is like an analogy we used on another episode was just driving, where your steering wheel is tied to the odometer or something like that. It's basically a really dynamical, complex kind of system.
Yeah, so when I took that class, we spent half the semester looking at the heat equation and the other half the wave equation. And so these are some canonical equations in math and physics.
And again, one more time, I did want to go ahead and revisit explaining partial as well as ordinary differential equations. And I like your analogy, Jonathan, but I think just to elaborate, basically it's a changing system. So whether you have a deceleration or an acceleration of a car or a change in voltage or what else?
Well, I think you could actually model any system using something like if you imagine each variable is a person, and you imagine these or a type of person, like maybe one person's name like Albert and the other one's name Beth, and these are your two variables. And anytime they bump into each other, they have to trade some stuff that they have in their pockets, and there's like a constant trade rate. Like, is that too complicated? I think that's too complicated, but it shows you the complexity of these systems.
I would even just use the wave equation itself. The wave equation from a strictly math perspective, you have 2 time derivatives and 2 spatial derivatives. But to think about that simply is, how am I changing in space at the same time that I'm changing in time?
And the heat equation kind of shows how heat gets distributed. So if you start, and correct me if I'm wrong here, but if you start, like, let's say I put an iron on a piece of metal, you're going to have a really hot, let's say it's like a super hot iron, and I did it really quickly. You'd have like a little hot piece of metal the shape of the size of an iron. But then the metal starts distributing the heat around it, and it starts going everywhere. And that's the heat equation, right?
Yes.
And the wave equation is, let's say you have a little shallow pool and you slap it, and then you have all these little waves going everywhere.
Exactly.
And that's how you learn, and you learn to describe that mathematically in these courses.
Yes.
Now, what's hard about it?
The fact that you have multiple variables changing. So in ordinary differential equations, you have one variable that's changing. They're still hard, but in partial differential equations, you have, like I said, you have space is changing while time is changing. And so you just have like really complicated dynamical systems that many times are not solvable.
And you don't just mean not solvable like it's too hard for most people. You literally mean it cannot be solved using what's called a closed form system, right?
Yeah, exactly. So closed form, that's like, in my research, we're looking for closed form expressions for things. But, in real life and, the vast array of types of math functions, most of the time you cannot get a closed form solution.
The way that I like to think about it sometimes is if you have a bunch of ingredients, you can sometimes combine a couple and find that combination at the store. So you get some tomatoes, you get some onions, you could find some tomato sauce at the store, but most of the time you're going to be throwing things together you cannot find at the store.
I was honestly hoping you'd give some more examples of that.
Sure, you get some chocolate, you get some chili, you find some mole, but you take some chocolate, you get some pears, you can't find that at the store.
That actually sounds really good.
I know it does, doesn't it? So that was one of our most interesting interviews that we've conducted, I think.
I think so. Yeah, I was very, very thankful that Frank agreed to share his story with us. I found it really inspirational.
Now, for all you fans out there, there's going to be some new changes coming down the pike. We can't talk about them specifically, right?
That is absolutely correct. There are definitely some changes, and we are waiting before we feel that we can talk about them publicly.
Yes, but just stay tuned for the same great content that you've always loved.
And you will always be able to find us wherever great podcasts can be found.
We won't make
When you need mealtime inspiration, it's worth shopping Kroger, where you'll find over 30,000 mouth-watering choices that excite your inner foodie. And no matter what tasty choice you make, you'll enjoy our everyday low prices, plus extra ways to save, like digital coupons worth over $600 each week. You can also save up to $1 off per gallon at the pump with fuel points. More savings and more inspiring flavors make shopping Kroger worth it every time. Kroger, fresh for everyone. Fuel restrictions apply.
it hard for you.